It's science, but not as you know it. The Naked Scientists.
Hello, welcome to The Naked Scientists this week with me, Chris Smith, and also with Helen Scales.
Hello.
Now, in the programme this week, we're going to be finding out how a gap in the clouds might in future predict earthquakes, also how seahorses are riding up the Thames in significant numbers again, and a hard-hitting story now. Scientists have discovered why those balls that go straight up in the air off the bat are so hard to catch. And we'll be catching up with those stories in just a moment. Helen.
Thanks, Chris. And this week, we're also looking at the science of the sun. We'll be turning back time 150 years to the largest solar storm that's ever been recorded, which wiped out communications on Earth and caused boats to get lost at sea because their compass needles were spinning around all over the place. Why did it happen? And what's the chances that it'll happen again? We'll also be looking into the contentious link between the sun's activity and climate change. So, is global warming all down to natural variation in the sun? We'll be finding out. Plus, there's a breath of fresh air in this week's Question of the Week.
I tend to drive with all the windows closed and the recirculation function engaged. If the car were a perfectly sealed container, how big would it have to be for me to survive in it for a day?
And you can find out how long that person has to live inside the car a little later in the show. Hopefully it'll be long enough to hear the answer. Chris.
Thank you very much, Helen. So if you've got a question for us about the science of the sun, do get in touch. Email chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's take a look, as we always do, at some of this week's top science news stories that are broken out in the world of science. This one caught my eye, Helen, for the simple reason that earthquakes are important. It's a piece of research published in the rather obscure journal International Journal of Remote Sensing, and it's a couple of Chinese guys called Guanmeng Guo and Bin Wang, and they're both working at Nanyang Normal University in Henan. And in this paper, they say they've been looking at geostationary satellite images of the Earth, and specifically at clouds. And they noticed that in 2004 and 2005, over Iran, which was, if you cast your mind back to 2004 and 2005, home to a very big magnitude 6+ earthquake on 2 occasions, they noticed that there was a very strange gap in the clouds that opened up over the southern reaches of the fault in Iran. And what was bizarre is that this gap stayed there despite the fact that clouds were moving on all sides of that gap and should really have obscured it. And 60 days after this gap in the clouds appeared, there was an earthquake there, on both occasions. Now, it could just be a load of hot air, but their theory is that some kind of heat coming out from the seismic activity that was making that fault get ready to move could have risen in the air and caused the water vapour in the clouds to evaporate, making that space. Or there's another theory which has come out of the NASA Ames Research Center in California, which is that perhaps when rocks are squeezed together as they would be in some kind of fault like this, perhaps they produce some kind of ions or some other kind of particles that go up into the air and they in some way disperse clouds. It's a bit contentious. There was a bit of research done in Russia in the 1980s that claimed something similar. Some Russian scientists said they'd seen a similar observation, but it was never proven. And so it could be that it is just a coincidence, but there might really be something in it.
And it sounds to me like this is the kind of thing we could test, because surely we could look at other geostationary, remote-sensed images and look at other events when there were earthquakes and see if there's a similar pattern. And maybe, yeah, it could be a way of predicting them. I mean, is there any more plans? Do you think perhaps other people will look at this now and kind of see if it really is going on, perhaps?
Seismologists are sceptical about it, but it could be that if this does give us an insight into at least the behaviour of some earthquakes, that even if you only predicted a small number, you could predict some. It would be a warning. And since some of these earthquakes kill thousands of people, it could be a very useful way to try to avert the danger.
And obviously,
it certainly deserves looking at, doesn't it?
I think certainly, and if we just understand more, perhaps it will point us in a direction that will let us understand if it is heat or ions or whatever it is. Well, now, how could I possibly resist this week talking about a story that hit the headlines, which was that the discovery of seahorses, those wonderful creatures of the sea, living in the Thames estuary in London, not very far from where we are here in Cambridge. Now, over the last 18 months, researchers from the Zoological Society in London have encountered a population of short-snouted seahorses. These are these tiny creatures which would lie quite happily on the palm of your hand, the lovely little things. One of my absolute favourites. They've been seen as far east as Dagenham, where the tide is still bringing in enough salty water, because seahorses don't actually live in full fresh water. They have been seen in the Thames in the past, but really not in so many numbers, so just one or two have turned up. A little bit like when the whales turned up in the Thames a couple of years ago. And just like that, the Londoners are, I think, quite proud of their newest aquatic neighbours, and it's a really good sign that despite being so notoriously mucky and polluted, the waters of the Thames are actually really cleaning up and doing much better than they used to. In fact, they're home to other things like porpoises and seals and otters, and so it's really, not a bad place to live. And the really good news is the reason that the Zoological Society have released this news about the seahorses is that they're now protected in the UK under the Wildlife and Countryside Act, which means it's now illegal to take them from the wild, and you're not allowed to damage their habitat either. So, we can hear about them being there, be proud about it, but leave them well alone, I think.
Why are seahorses viewed as such an important canary in the cage for rivers like the Thames?
They are
Why
very
not other
sensitive.
fish?
They're very sensitive and they are quite rare. So to spy them, they're sensitive to clean water and to intact habitat. They have to have seagrasses and sort of submerged vegetation like that to hide amongst, because they can't swim very fast. They have to have things to hold on to. And they are the first things to go, really. That's what we've seen in other places, that they are very sensitive. So if they're there, it means things are doing pretty well.
Could it also mean, rather worryingly, that it's just that the currents are changing because the ocean's getting warmer, people are worried about global warming, and this is meaning that fish which would normally not come in significant numbers to our waters now are, and that includes seahorses?
Yeah, that is another possibility, and it's something we need to consider. These are species that are much more common further south in the Mediterranean. There's actually another species of British seahorse which is also protected, the long snout seahorse. That's the same thing. So it's a question. We don't know. We can't be sure. It's something to bear in mind, but I think, it's all part of a bigger picture of things that are changing, really.
So we should take it as encouragement until we prove that maybe there is something more worrying going on. And then...
I think in itself it's nothing to worry about. I think it's nice, but it could be part of a bigger jigsaw of things that are changing.
Well, let's talk a bit about Bend It Like Beckham. Couldn't think of anything better to describe this as, but there's a group of scientists in America, Alan Nathan and Terry Barhill, and they've got a paper coming out in the American Journal of Physics, and they've been solving that well-established conundrum of why is it that when you go to a baseball game or a cricket game, you see the ball come off the bat and it goes straight up in the air, one of those pop-up balls. And it looks like it should be the biggest cinch in the world to catch it, doesn't it? So why do the fielders struggle so much? And then the crowd go, drop that one, can't believe you fumbled that. Why didn't you catch it? Well, it's really hard to catch, and now we know why. What these researchers have done is to model the trajectory of these balls as they go up in the air and then come down again. And it's not as simple as it looks, because when the ball leaves the bat, it has a tremendous amount of backspin. In other words, the ball is spinning in one direction very, very fast. And when a ball is spinning, it drags with it a sort of sheath or a coating of air from the surrounding air. And when the air is pulled around the ball in this way, because the ball is pulling on the air, because of Isaac Newton's third law, for every action there's an equal and opposite reaction. If you're pulling on the air pushes back on the ball in the opposite direction. So that's why spinning things change their trajectory. So when the ball goes up in the air, when it initially travels very, very fast, the air doesn't stick onto the surface of the ball very much. But as it slows down and the air begins to stick on a lot more, it begins to exert this subtle pulling effect on the ball. And this alters the trajectory at the top and initial part of the descent of the ball's flight, so that when the person on the ground looks at it, they think it's going to come down in a certain direction, because we're pretty good at predicting where things go under gravity. But it doesn't. And so when they superimposed their simulation on where they thought that people would think the ball was going to go onto what people actually do on the sports field, they found it matched up. So that's why people do that interesting dance to try and get their hands under the ball when they're on the sports field, to try and catch those really difficult balls.
Is there any way we can use this to teach ourselves how to actually catch it, or is it really random as to which direction it's going to move in terms of the spinning? It's just a random
really
spin
hard.
in any direction. So
the reason David Beckham's corner kicks are so lethal is for exactly the same reason, that they have this thing, it's called the Magnus effect, this force of the air pushing the ball along, named after a guy called Heinrich Gustav Magnus, who was working on this in the 1850s, actually. David Beckham kicks a ball and gives it a huge amount of spin. When it moves very, very fast initially, the spin doesn't make much of a difference to the trajectory of the ball, but as it slows down near the goal, suddenly this kicks in a big way and pushes the ball into the top corner of the net.
But it's too late and you can't get to the ball in time if you're the goalkeeper.
And the human brain is very bad at predicting spinning things and where they're going to go, for the simple reason that we've evolved to have gravity in our lives, and we know how to predict and compensate for the effects of that. We know how gravity affects the motion of objects, but when they're spinning, the human brain finds that very hard to process, so we find it really hard to predict.
Well, there you go. Now, for my last story, I'm going to take things down on a very tiny level to that of bacteria. Now, because researchers this week have revealed a brand new way of using bacteria to help mop up harmful chemicals in the environment, like pesticides. Now, using microorganisms to clean up the environment, there's something called bioremediation. It's an idea that's been around for a while, for example, to help things like mop up oil spills. But now a team of scientists from Emory University in Atlanta in the US, led by Justin Gallivan, have genetically engineered E. coli bacteria, those common bugs that live in our guts, so that they will detect particular harmful chemicals, swim towards them and gobble them up. Now, naturally, these bacteria have receptors on their cell surfaces that detect chemicals in the environment that they're interested in. Usually that's things like food. The chemicals will trigger a chain of events that activates a tiny little whip hair called a flagellum, which whizzes round and round and pushes the bacteria forwards towards the source of the chemical. Now, what the team did was they knocked out the gene in E. coli that makes them move forward and added in a segment of RNA called a riboswitch, which essentially responds to the presence of a particular chemical. And this time they picked something called atrazine, which is a pesticide. And when the bacteria notices that chemical is in the environment, it switches on the flagellum and it swims towards it. And then when it gets there, it metabolizes it into harmless waste products.
So this is a good way of making bacteria home in on where the muck is and then break it down.
Yeah, exactly. That's what it is. I mean, we don't yet know if this is going to work in the environment because they've just been doing this in Petri dishes. But it does have a lot of advantages, and it looks like you can make it very specific to all sorts of different chemicals. So it's a great way of mopping up those pollutants in the environment.
Because someone I was speaking to the other day, I said to her, how can bacteria exist that would break down, say, an oil slick? Because that's what she's working on. And she said, well, there have been natural oil seeps around for millions of years, and therefore bacteria, wherever there's a possible source of food, because oil is a source of food, it's got lots of carbon in it that bacteria can metabolize if they know how. So there have been bacteria that have evolved to break these things down. It's just a question of finding them and then engineering them so we can use them to clean up the mess we make of the world.
Bacteria do all sorts of crazy things. You have rock-eating bacteria and all sorts. I think they can make do with anything you give them, actually.
I think someone came up with a concrete-digesting bacterium as well, but someone said you should be very careful if you get that near Croydon or Birmingham. Could be bad.
I don't know, maybe good.
It's The Naked Scientists with Dr. Chris and Dr. Helen. We're talking about the science of the sun this week, and on the way we'll be exploring one of the biggest solar events in history and how it wiped out communications on Earth. We'll be finding out about the solar physics behind that, and also the link between climate change and the sun's activity. Is there a link there, or is it just a load of hot air? We'll be finding out. If you'd like to join in with today's show, you can get in touch. It's chris@thenakedscientist.com.
Laying the facts bare, The Naked Scientists.
You're listening to The Naked Scientists with Chris and me, Helen. Now it's time to go to Ben and Dave. They are hiding away for some reason in a dark room in Cambridge University for this week's Illuminating Kitchen Science.
For Kitchen Science this week, Dave has kept me completely in the dark about what we're going to do. And I mean that quite literally. In fact, I can't see a thing. We're somewhere in the Department of Pathology. Dave has shut me off in a lecture theatre, and I can't see anything, but I can hear something. I think there's someone around. Is there anybody there?
Hello.
Well, I found a couple of people. What are your names?
Jessica. Katie.
And what on earth are you doing in a dark lecture theatre?
We're here because Dave told us that there's an experiment here.
So Dave is in here somewhere?
Yes, over there.
Hello, Ben.
Ah, hello, Dave. Right. So we're in a pitch-dark room for Kitchen Science this week. What on earth are we going to do? Can you shed any light on it?
Yes, Ben. We're going to see what happens if you mix static electricity and a light bulb.
OK. Well, usually you plug a light bulb in and use non-static electricity, don't you? So we'll have to see how this works. Where are we getting our static electricity from?
All we need for this experiment is a balloon, an energy-saving light bulb, and some hair.
I can see that Dave has a balloon and a light bulb. Do either of you have any hair we can use?
Yes. Yeah.
What do we need to do first?
The first thing you need to do is blow up the balloon. So, Katie, could you do that?
Yes.
So she's got a balloon blown up. Do we need to tie it off?
Yes, if you could tie it off as well, that'd be brilliant.
Are you OK with tying knots in balloons?
No.
Dave, do you think you could join in and help?
OK, I'll do that if you want.
So Dave's just tying off the balloon now. And this is all we need, just one balloon?
Just one balloon and an energy-saving light bulb, that's all you need. Now, Jessica, what I want you to do is rub that on your hair and see if you can charge it up as much as possible.
We're really sorry if it spoils your hairstyle.
And then what I want you to do at home is get to a very dark room, get that balloon, and then wave it very, very close to that light bulb and see what happens.
So switch off all your lights at home, get an unplugged energy-saving light bulb, preferably one that works, I guess, not a dead one.
Probably would work with a dead one, but I'm not sure. I've never tried it.
Get your statically charged balloon and wave it back and forth very close to the light bulb. Now, girls, what do you think will happen?
I think the balloon might burst.
Fair enough, so it looks like the balloon might burst, but we will come back to you later on in the show to let you know what happens.
Right, we're going to leave those guys in a very dark room making strange noises, while you at home, I hope, will have a go with rubbing a balloon on your own heads, ruining your hairdos, switching out all the lights and waving it near an energy-saving light bulb, which we should all have, I'm sure. So let us know what happens. And if you've got any other questions at all about the science of the sun or anything at all about science, email us on chris@thenakedscientist.com.
And Dave also has as a favourite rubbing centre for his balloons his leg, because he's got very hairy legs. So if you're bald or follicularly challenged is the appropriate way of saying it, then you can also use a leg. Now, anyway, here's a question. The universe is a very big place, so if you've only got a small number of telescopes with which to look at it and limited resources to analyse the data you collect, inevitably there are going to be lots of important questions that are going to go unanswered. So how do you solve the problem? Well, it turns out the answer is by professional astronomers teaming up with amateurs all around the world and asking the amateurs to do some of the observing for them. And that's exactly what Dr. Pamela Gay from Southern Illinois University at Edwardsville has been doing.
I work with the American Association of Variable Star Observers, which, while it has the name American in its title, is actually an international organization of observers. We have people from all around the world, amateurs, who like to go out in their backyard and look at stars and measure how bright they are. And it sounds like just a fun game, but for scientists, this is amazingly powerful. I study a type of star called RR Lares. These are stars about 0.6 times the mass of the sun that aren't stable, and they get larger and smaller and change in brightness as they do this. When Shakespeare said inconstant stars, he was exactly right. They're inconstant. They do this over less than a day. And to fully understand them, I actually need about a month's worth of data because the night is short and I can't always get the entire light curve, the entire change in brightness from bright to faint.
Is that because there's competition for the telescope time, so you can't literally hog it for that long to see the full periodicity of what these stars are doing?
I can often hog it for one night, but then the sun comes up before I'm done. So if I can get, say, the first 60% of the light curve one night, I might be able to get then from 3% to 63% the next night, and I have to go night after night before the star cycles all the way around. And they're not going to give me 10 nights. But if I observe in the United States and I can find an Italian amateur astronomer with a 12-inch telescope in his backyard to observe for me there, and then I can find an Australian with a telescope in their backyard and my object's far enough south that the Australian can see it, my star can get handed off around the globe from person to person.
So what's the idea here? That you will recruit people who are doing astronomy as a hobby and get them into your project so they're contributing to your research?
Exactly. This is an opportunity for someone to take their hobby, their love of just going outside and watching the stars and how they change, and actually contributing to our knowledge of how the universe works. The particular stars I'm working on aren't well understood, and until we can observe probably about 100 of them in deep detail, we can't make any heads nor tails of them. We just know they're behaving oddly.
What are you asking these people to do, and how do you know you can trust their data? Because as a scientist myself, I'm a total perfectionist.
Yeah.
And unless I've done it myself, I get terribly worried that it's not trustworthy. So how do you get trustworthy data out of people who you've never met?
Well, the trick is that you have to calibrate things in multiple directions. If I have a field of stars and they can take a digital picture and catch 4 stars in it, one of them is my target star that's changing in brightness all the time. And the other 3 are constants. And if I know those stars have values of 10, 10.4, and 11... and
this is the brightness, presumably.
This is the brightness. We measure brightnesses on a scale of 0 to, well, as dark as it gets, where 0 is the brightest. The human eye cuts out around 6. You can get with a typical backyard telescope down to about 14, and the numbers just keep getting bigger. If I know for certain the numbers associated with 3 of the stars, and I know the 4th one varies, and their measurements of those 3 are bang on the same the entire time, I know I can trust the results.
So you're asking people to send you pictures or just brightness measures of the stars, which you can then use to calibrate their results?
What I ask them to do is take the images and make the measurements of this one is 10, this one is 11, and this is what your variable star is, and just send me an Excel spreadsheet. And then I combine all these Excel spreadsheets. A couple of years ago, I did a campaign. I got, in 3 months, over 8,000 observations. And they weren't all perfect. But out of those 8,000 data points, I got several thousand that allowed me to solve a problem star I'd been struggling with since 1992.
This is like the astronomy equivalent of the SETI at Home project, isn't it, where you're just analysing huge amounts of data that professionals could not have the time to trawl through. So you get people to just do something for you.
This actually takes that model and turns it on its head. With SETI at Home, with Galaxy Zoo, the scientists are acquiring all of the data, and then with SETI they're saying, please let me abuse your CPU processor on your computer, and it will tell me the analysis. With Galaxy Zoo, they're saying, we have all these pictures, please, can you do the analysis for me? In my case, I'm going, I want to do the analysis, but I don't have the data. And so I'm asking them, can you please use your telescopes to get me the data I need?
Astronomer Pamela Gay explaining how amateur astronomers can team up with professionals to do cutting-edge research. She was in Cambridge this week to take part in a meeting between the AAVSO, that's the American Association of Variable Star Observers, and their UK counterparts, the British Astronomical Association. Now, as luck would have it, I also managed to track down one of those amateur astronomers who's been helping Pamela with her research, and I found him in the Castle Pub.
My name is Jerry Samolik. I live in Greenfield, Wisconsin, USA. My astronomy started probably late 50s, early 60s with the beginning of the space program. I still have an article in a magazine called Space Journal, 1958, covering the launch of the first American satellite. So I guess I've been a fanatic since childhood.
So you're just really interested in astronomy and space science. You're not a professional, but you do a lot of this stuff.
Correct. Actually, by profession, I'm an engineer, but I've been observing since I was in high school. In my backyard, I've got one flip-top observatory with a 10-inch LX200 CCD camera. The entire building is only 3 feet by 4 feet, so I can't get inside of it. It's just enough to house the telescope. Once I get the thing started, I set the autoguider up and I go to bed.
How many people in America and elsewhere in the world do you know of, through your connections, that do similar things to you, that are doing pretty high-level astronomy, but from the home?
Well, the number of people, it's hard to count. We have 3 active observers in Italy. We have several in the United States, maybe half dozen. We have one in Australia. What we try to do is coordinate our efforts where the Italian observer will get on a star. He'll send me an email. It's still noon my time. He's telling me what he's observing, so I know what target I can set up that evening. Then as the Earth rotates, I'll carry the star across. For southern stars, sometimes we can pass one off to Neil Butterworth down in Australia, and so we can get more than a half a revolution of the planet on one target.
You're doing pretty high-level work. Do you struggle to get professionals to take you seriously, though?
I don't think so. The organization I belong to, the AVSO, has always been in very high regard of the professionals, and it's always interesting to go to our meetings because we'll have amateurs giving programs and professionals listening to them.
So what are you looking at the moment?
This time of year, I'm working on a few RLA stars. I got one I'm working on in Cancer, and I'm just picking up one AR Hercules that's just starting to come up in the evening that I can run throughout the night. That's been a star I've been observing visually since probably the early 1980s. It's got a very interesting dual mode that it pulsates in, and we've got a kind of a handle on it, but every so often I see something that's out of the ordinary, and I'm just trying to see if I can find that happen again.
It was Jerry Samolik explaining how amateur astronomers like him can make powerful contributions to science just by helping professionals with their observations. And Pamela Gay, who you heard before that, was telling me that if you'd like to find out a bit more about the AAVSO, that was the body that Jerry's a member of, then you can also get involved with them, and their website address is aavso.org.
I've got a quick email here from Keith who says, thank you so much for the podcast. He listens to them on his tube journey on his way home and has interesting things to tell his kids, James and Hazel, when he gets home, which is lovely. And Hazel has actually asked a very clever question. She's only 7 and she wants to know why exactly it is that white light reflects light and black absorbs it. She knows it does that, but why? It's a very good question. I've never thought about
especially
why.
From someone who is 7. I think we're destined to have Einstein's next generation there. Well, if you think about what light is, light's a wave, and so it's an electromagnetic wave which wiggles its way through the atmosphere, through space, and when it hits something, if it hits something transparent, the wave hits that substance and it goes through it. And as it goes through it, the wiggling of the wave makes the particles in that substance wiggle as well, and that includes the electrons. Now, if the substance is transparent, the wiggling of the electrons regenerates the wave of light as it goes through the substance, albeit with a time delay, which is why the light slows down a bit on its way through. And then when it goes out the other side, it's recreated again with no loss of energy. But what about if the substance isn't transparent? In other words, it's opaque. Well, of course, it reflects light, and that gives it its colour. If it reflects no light, it's black. And we recently featured on the show the darkest substance in the Guinness Book of Records ever, Poulikel Al-Jayan, produced this substance. He's at Rensselaer Polytechnic, and the way he did that is by producing these nanotubes, a forest of bamboo-shaped nanotubes. These are tiny skeleton tubes, or like straws of carbon, and they're literally thousands of times thinner than a human hair. And by making a sea of these things, when light goes down into this, even if one ricochets off a nanotube and bounces into another one, it just gets lost, it gets trapped inside, so nothing gets reflected. So that makes the substance very, very dark. And when light gets soaked up by a substance, basically what it's doing is all the energy, the vibration of the light, is making the atoms in that substance vibrate, so it's making heat. That's why solar cells that are made of black stuff get warm, because they're soaking up all the light energy and radiating very little out. When a substance is radiating other colours, what's happening is that some wavelengths of light, some wiggles, are absorbed and they turn into heat in that substance, whilst others are reflected. When they're reflected, basically the wiggling that they impart to the material creates another light wave of the wavelength of the colour that you see. So that's why it reflects light of that particular colour. With white, the substance is very good at reflecting all wavelengths of light, which is why if you add all the wavelengths of light together, you see white. That's why it looks white. And that's why water is clear when you shine light into it, but snow crystals are white because the water, when the light goes through it, can pass straight through, but with snow crystals, lots of tiny particles of snow mean that the light gets bounced around all over the place, so all the wavelengths get returned to you, so it looks white. So I hope that answers Hazel's question.
So it's all basically about what it's made, what things are made of, and how they vibrate. Really, the difference.
Yes, there will be different substances and different molecules which will soak up different light waves of different wavelengths, different frequencies, but not others. And different coloured lights have different frequencies to each other, and some will be soaked up by the surface, and others won't.
Well, thanks for your question, Hazel, and do keep them coming in. If you have any more questions to ask us, then you can email us, chris@thenakedscientist.com.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
It's The Naked Scientists with Dr. Chris and Dr. Helen. We're talking this week about the science of the sun and astrophysics. And to join us now, we have Stuart Clark and Chris Davis. Stuart Clark is an astrophysicist. He's also previously an editor of the journal Astronomy Now, and he's recently written a wonderful book which is called The Sun Kings, and it tells an amazing story which he's going to share with us in a second. And Chris Davis is a researcher at the Rutherford Appleton Laboratory over in Oxfordshire, and they're actually studying the sun up close and personal with an amazing mission involving some satellites, and he's going to be joining us as well. But first of all, let me introduce you to Stuart. Hi, Stuart. Thank you for coming in.
It's my pleasure.
So tell us about this story, because we view the sun as this highly predictable and stable thing. You know, you get up in the morning, it's always there, but the evidence is it's not as stable as we might think.
Well, indeed, the sun is a highly variable cauldron of the most intense magnetic activity. So if you go back in history, you can find times when there have been extraordinary events that have taken place on the sun via its magnetic field. And as you say, the Sun Kings is about what appears to be the most violent of these storms in history, and that took place on September the 2nd, 1859.
What happened?
Well, imagine this. 2/3 of the Earth's skies erupt with the most incandescent, blood-red aurora, the kind of things that you see in the sky usually when you go up to the high polar latitudes.
So the whole sky just goes bright red like it's made of blood?
In this case, yes, that's what most of the eyewitness reports suggest. And worse than that is that there were other times when there seemed to be bolts of white light flying upwards and exploding with sort of silent brilliance in the heavens. It was just the most amazing cataclysm that engulfed most of the Earth's skies.
This is the 1800s. People must have thought the Earth was coming to an end.
They had absolutely no idea what was going on at all, and there was a sinister side to this story as well, because at the time that the aurora lit the sky, so the telegraph network across the world went down. It stopped functioning, and it stopped functioning in the most spectacular of fashions. Electrical currents surged along the wires into the offices. The sparks flew from the equipment, offices were set on fire, some of the operators were stunned unconscious. The whole of the global communications network, as the telegraph was at the time, was taken down. And at the same time, every compass on the Earth went haywire. So in an instant, and for reasons unknown to anybody, global communications and navigations just stopped.
Did people have any clue as to what was going on? There must have been massive speculation. People must have thought, wow, the end of the Earth is nigh here.
Yet one person was in the right place at the right time, the kind of coincidence you couldn't get away with writing in fiction. And that person was an English amateur astronomer called Richard Carrington. And he was working in his observatory at Red Hill, and he was engaged in his mission was to study the sun for a full 11 years and chart the comings and goings of dark blemishes on the surface of the sun called sunspots. And it was known that the more sunspots there were on the sun, the more unreliable the compass readings were. And so there was this clue that somehow the sun was magnetic, and that magnetism could reach out across space and affect the Earth.
So how did Carrington connect this amazing event you've been describing with the sunspots that were going on?
What happened was at just before noon on the 1st of September, he was looking at a massive sunspot, about 10 times the diameter of the Earth, this sunspot, and he saw two brilliant beads of white light appear above the sunspot. He realised that this kind of explosion, for want of a better word, had certainly not been charted or recorded before. And as he traced this, it lasted for a few minutes, and it passed across the top of the sunspot and then disappeared. Well, he went to try and find other astronomers to see if they'd seen something like this. And although he couldn't find instantly anybody else who had seen it, at the Kew Observatory in Richmond, they had magnetic needles studying the Earth's magnetic field, and at exactly the moment that Carrington saw his flare, so the magnetic needles had jumped. It was just as if the Earth's magnetic field had been struck by some mighty fist, or it was like a bell being struck by a hammer, and it was still ringing. And that night, the magnetic needles continued to jitter and get stronger, and then suddenly the skies burst into these aurora.
How long did this phenomenon last for, with boats not knowing where they were going, people being electrocuted, offices catching fire?
Well, the Earth had been in the grip of magnetic squalls, for want of a better word, on and off for the best part of a week. And this one lasted over 24 hours.
So Chris Davis from the Rutherford Appleton, what was going on the sun when all this was happening?
Sounds astonishing, doesn't it? I want to thank Stuart for giving me the most exciting introduction I've ever had, I think. What happens, we now know, is that the sun has a magnetic field, but the sun is a fluid, and so unlike the Earth, which is a solid body, when the sun rotates, it churns and twists that magnetic field up with it. And the sun also has a stream of particles coming away from the sun, called the solar wind, so that part of the sun is blowing out into space the whole time. Now, when you twist and wrap up the magnetic field, which is what is happening during the solar cycle, you actually store energy in the magnetic field because you're stretching it. It's like winding the propeller on a rubber band on a model aircraft. You're storing energy by twisting it and stretching it. And when that magnetic field is twisted and contorted and can take no more, the magnetic field reconfigures in some way. That can release energy in the form of light, which is the flare. The flare is given off by particles as they're accelerated very rapidly during that process. And it flings very hot, energized, electrified gas into space along with the sun's magnetic field. And of course, if that arrives at the Earth, it can interact with the Earth's magnetic field and allow that material to interact with the Earth's atmosphere, which is what causes the aurora. At the same time, electrical particles flow in the upper atmosphere because there's very little resistivity in the upper atmosphere, and so these particles can flow very readily. Those induce currents in the telegraph wires that are on the ground. And that causes surges of electricity in those which we have heard have caused such a disaster at the time.
So, Stuart, as people experienced this, how did their understanding build from 1859 when this event actually happened, so they began to get towards understanding what they'd experienced?
Well, it was a long process, and many of the people at the time, their first thoughts were just utter disbelief. They had become extremely used to the idea that gravity was the only force that could really communicate itself across space. And here was the what seemed like the suggestion that magnetism could do the same. This was the flare, the Carrington flare, and the subsequent magnetic storm was seen before they even had a working theory of electromagnetism. That came along with James Clerk Maxwell. And here's the fascinating point about this, is Maxwell's field theories seemed to prove categorically once and for all that this magnetic energy couldn't come from the sun, because the sun couldn't radiate enough energy to cause the aurora and the movement of the compass needles that were being seen on the Earth. That only became unpacked in the early decades of the 20th century, when people started to realise that particles could carry electrical or magnetic fields, and that you didn't have to radiate huge waves of the energy all throughout space. In fact, you could sort of send them in specific directions, like little magnetic cannonballs as such.
And Chris, have we had anything similar to this happening since the 1859 Carrington event?
That's certainly the biggest storm. There is another storm more recently, in 1989, I think, where there was a storm which, of course, had similar effect, large auroral disturbances, and induced currents, not in the telegraph system, of course, because by this time we're not using the telegraph, but we did have a national grid, and those countries such as Canada and Alaska, whose national grid stretches over large areas, have long cables, and it induced currents in these, which again blew up transformers and large areas of Quebec, for example, without electricity for many days.
I've got an email here from Racy Stepanovic, and he's wondering how it is that these pulses do the damage that they do.
The reason is that when you have this magnetic field releasing, it actually releases an intense storm of particles. It's called a coronal mass ejection to scientists, which is a very dull name for anything, but actually it's 1 billion tons of material travelling at 1 million miles an hour. It contains about 100 times the energy of the entire world's nuclear arsenal. And although it's spread out over an extremely wide region in space, if the magnetic field that contains is in the opposite sense of the magnetic field on Earth, then we all know from school that magnets of opposite polarities attract, magnets of similar polarities repel, and if they're opposing polarity, the two magnetic fields can interact, and that allows all this hot material to start interacting with the Earth's magnetic field and the atmosphere.
And Stuart, something similar happened in 2003, didn't it? Only that time, luckily, it missed us.
Yes, there was the Halloween flares of 2003.
How appropriate.
Yeah, it really, really was. It took place over about a 14-day period, and there was one flare on November the 4th, which was colossal. Luckily, it just happened to be pointed virtually away from us in space. But there were two flares a little bit earlier, and on October the 28th and October the 30th, and they were large and they were pointed towards the Earth. They were perhaps about 5 times smaller than, say, the Carrington flare. But for the first time, the civil aviation authorities actually diverted aircraft in case, as a precaution, in case the passengers.
So what aircraft were brought down into a lower altitude, for example?
Yes, they were moved down into lower altitude, so there was more air above them to act as a cushion. But also they were brought away from the polar regions, because in the polar regions that's where the magnetic field of the Earth turns back into the planet and the core where it's generated, and that's where solar particles from these ejections can be funneled into the atmosphere, and that's what causes the aurora. So the aircraft were brought away just as a precaution.
Thank you very much. That's Stuart Clark, and his book is called The Sun Kings, and it's absolutely stupendous. you won't mind me recommending it, but don't buy it if you don't mind insomnia, because you won't be able to put it down. I've got a very quick question here. Paul Taylor's on the phone, wants to ask Chris a question about the death of stars. Hi, Paul.
Hello there. Now, I understand the sun, it gets its power from hydrogen fusion and gradually fusing together bigger and bigger atoms. Towards the end of its life, or particularly if it goes supernova, and it blasts all those heavier elements out into the surrounding space. Now, I've often heard it said that this is what seeds the next generation of stars. It just sounds as if it's the spent star fuel that goes to create the new stars.
A bit like shoving your sort of exhaust pipe of your car into the fuel tank of your car, isn't it? Chris, what do you think?
Well, it's certainly true. What happens is that when you burn hydrogen to form helium, the star is the consequence of an equilibrium of forces. You've got the gravitational collapse of that body of gas pulling inwards on it, and you've got the heat generated by the nuclear reaction in the middle pushing the star out. And you've got to have an intense amount of pressure in the middle to force hydrogen nuclei close enough together to form helium. And there are various other burning cycles. You can burn helium to produce carbon, but eventually when all the fuel is used up in the core, there is no forcing out of the star, and so gravity wins out and it collapses the star in on itself. When this happens, of course, you get very briefly, you get very dense, a large increase in density in the star's core, and that can generate these much heavier elements, and then the star will explode. So
you could look upon it as the stars are almost like the uteruses of the universe. They give us everything that we're made of.
Well, that's certainly true. But the star isn't going to be completely burned to the other element. There is going to be a large amount of hydrogen. And also, the universe is still very much dominated by hydrogen gas, which is the primal fuel for stars. So that dust, that matter, the heavier elements will be spread out into space. And some of it will contaminate the next generation of stars. So as another cloud starts to collapse together under its own gravity, because there is this sort of a gravitational cloud of material, you'll get some of that heavier element polluting, if you like, the new star that's formed, and it won't be pure hydrogen to start with. And so you'll still have the majority of the gas will be hydrogen, but you'll still have some of these heavier elements combined in with it.
Thank you very much. That's Chris Davis from the Rutherford Appleton University. Chris and Stuart are both here with us, so if you'd like to join us on the show, it's chris@thenakedscientist.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
You're listening to The Naked Scientist. Now, we've been talking about solar activity and how that can change over time. But there's another thing that's involved with solar activity that's been on the news a lot lately, and that's this link to climate change, with people thinking that actually there's a link, perhaps, between the sun and cloud cover, which might be what's causing changes in temperature. Now, Professor Terry Sloan has looked at this relationship, and he thinks it's much more complicated than that. And in fact, we have Terry on the line right now. Hi, Terry.
Hello.
Thanks for joining us. Now, what is this theory that there could be a link between solar activity and cloud cover?
Well, a few years ago, a group in Denmark observed that the satellite data on cloud cover decreased. That was about 1990. And at the same time, they observed the cosmic ray intensity, the galactic cosmic ray intensity, also decreased. And so they saw this correlation between the two. So they hypothesized that the ionization from the cosmic rays was causing clouds. Now, if this is true, then since the cosmic ray rate has decreased over the years, over about 100 years or so, then we have less cloud cover now than we had 100 years ago. Therefore, that allows more sunlight to come to the Earth to warm the Earth and cause the global warming. That was their hypothesis. Now, this seemed to us to be a vast significance, because it means that the climate change is being caused by cosmic rays and not the carbon dioxide that the IPCC say. So we thought we'd better try and check this hypothesis.
So how did you start looking at that? How did you go into detail?
Well, the first thing was one of the things we did was just mentioned a few minutes ago. The solar flare in 1989 and the one in 2003. Not only did this cause huge changes in the aurora, but it spewed out a whole load of particles which interacted in the upper atmosphere and caused a big increase in the ionization in the air.
And crucially, did you see a big change in clouds?
No.
And so that was the clincher then?
Well, no, that was the first thing. That was the first nail in the coffin. Then we looked at a couple of other things. Cosmic rays occasionally go through quite a big decrease over a period of a week. They're called Forbush decreases. And we looked to see when these decreases happened, did the cloud cover also decrease at the same time or a little bit later? And again, we could find no correlation. So that was the second thing we looked at.
So have you come to the point where you can say, no, cloud cover isn't affected by solar activity to any extent that we can explain what's changing in the climate? Or is it something that we should still kind of bear in mind when we're thinking about what it is that's changing the temperatures in the world around us?
Well, we did a measurement of how much of the cloud cover could be caused by the cosmic rays, and our answer came out. We got an answer for that, and then we did a statistical analysis to say how big could the effect be, and we've missed it, and it came out to be about 20%. So in other words, about 20% of the changes in cloud cover are caused by cosmic rays, and that's an upper limit that we deduced.
And so if cosmic rays are having this effect, how are they having this effect, and could that change over time?
Can I interrupt you there? We didn't say that cosmic rays are having this effect. We tried to check the effect that was seen by the Danish scientists, and we all the evidence that we looked at did not corroborate their hypothesis. And it could be as high as 20% within the measurements that we made. But it was compatible with zero.
So the sort of bottom line here is that the efforts we're making to try to cut carbon dioxide are appropriate because that's our best contender for driving climate change at the moment.
Yes, that's correct. And therefore the Danish group, which effectively had challenged the conclusions of the IPCC, have no right to challenge the IPCC. That's the International Panel on Climate Change.
Thank you very much, Terry. That's Professor Terry Sloan with his new model on why it is that solar activity is not linked to cloud cover, and therefore he thinks that solar activity cannot be the key driver of global warming.
Well, I think the global warming debate is going to carry on. We have now in the studio with us Diana O'Carroll. Hi, Diana.
Hello.
So, have you got any hot topics? Do you think there is on climate change? Do you think it could be cloud cover, or do you agree with what Terry was saying?
Well, I just think we should probably think about air in cars more specifically, because this week I've got a question about being breathless.
Hi, this is Paul calling in from Hong Kong. I tend to drive with all the windows closed and the recirculation function engaged. This way I keep out the diesel fumes and dust. The flip side is I'm breathing in recirculated and progressively stale air. So my question is, if the car were a perfectly sealed container, how big would it have to be for me to survive in it for a day? I'm trying to figure out how long I can drive in a compact car without running the risk of passing out.
So if your car was perfectly airtight, and it would be pretty well engineered for that to be the case, what would happen?
I'm Gisli Jenkins. I'm a consultant respiratory physician at the University of Nottingham. The easy answer to this question is that you will never run out of air. You will just exchange the breath that you breathe in with the breath that you breathe out. But I guess what the question alludes to is how long you have to survive in that box before you die. Because what you're doing is you're exchanging ambient air with exhaled air. And the gaseous composition of the two airs is quite different. Ambient air has a CO2 concentration of about 0.5% and oxygen concentration of about 21%. Exhaled air has a CO2 concentration of 5% and an oxygen concentration of 13%. So what you'll do over time is you'll reduce the oxygen level in the air and increase the carbon dioxide level. And the problem is not so much the reduction of oxygen, but the increase in carbon dioxide. By the time your carbon dioxide levels in the air that you breathe in the box reach 15%, you'll effectively die. Assuming the box is about 4 cubic meters, it would take about 16 hours or so. But the reality is that you would actually start to feel ill and probably die a lot sooner than that. So actually, it could be down to sort of 5 hours.
Sadly for our prisoner, it's not so much a case of running out of air as poisoning yourself with your own expelled gas. It's a good lesson that it's always worth opening your window every now and then.
I've been a victim of someone with their own expelled gas. On our forum, of course, Merdidus Scientia, presumably mad scientist, came up with a brilliant answer and narrowed the time down to a very precise 4 hours and 20 minutes of survival.
That is very precise. Here's another safety tip to consider.
Hello there, my name is Clive Wilkins. I'm from Sutton Coldfield. I have a question. My dad always used to unplug the TV when lightning was nearby. Was this the right thing to do? Excuse the pun, what is the current advice? Thank you.
While you're pondering the security of your TV, spare a thought for those poor oil magnates with this question.
Hi, I'm Dr. Raj from Sri Lanka. My question is this. During the 1970s, we were told that oil would run out by the year 2000. Then new reserves were discovered, and now they say 2100 is when we will be starved of oil. Is it possible that we'll find more oil reserves in time to come? And why have we missed them before? Can the price of oil make smaller reserves economically viable? Thank you.
What's the best thing to do with your 42-inch LCD screen these days? And do you know of any secret oil reserves? Email me with their locations and your answers to Question of the Week at thenakedscientist.com or follow the discussion at thenakedscientist.com/forum.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
You're listening to The Naked Scientists with me, Helen and Chris. Now, I think it's time we switch the lights off again to find out what Ben and Dave are getting up to in the dark with this week's Kitchen Science.
Welcome back to Kitchen Science. We're still in a dark lecture theatre in pathology. We've got Dave Ansell with an energy-saving light bulb, and we've got our volunteers Jessica and Katie. You've been rubbing a balloon on your head to get it all charged up, haven't you? Is your hair a mess now?
A little bit.
We'll give it one more good hard rub. OK, Dave, we've got our charged up balloon. What's next?
Okay, first thing to do is remember which bit of the balloon you rubbed.
So which side you rubbed on your head?
Yeah, that's right. Now I'm going to give Katie the light bulb.
Katie, can you see anything special about that light bulb?
Not really.
Is that just because it's dark in here?
Yeah.
OK, I'm guessing, Dave, that it is an ordinary energy-saving light bulb.
Perfectly normal, nothing strange going on. I want Jessica to wave the side of that balloon which she's charged up and down very close to the light bulb.
OK, girls, so when you're ready, I want you to wave it about and let us know what happens.
It kind of makes the light bulb flicker a little bit with light. It doesn't light up if the balloon's still, but if he moves it, it lights up.
I mean, that's really amazing, Dave. It does light up. So what's happening?
You may have done a trick with a charged balloon before where you can stick it on a wall and it will stay there.
Yes, I've done that. You rub it up on your head for a while till the static builds up and then it just holds itself on the wall.
That's right, because the charge tends to attract things. Now, inside the light bulb, there's a very, very low-pressure gas. And inside that gas is a load of atoms of mercury floating around, and some of them will be a bit charged. When the balloon gets near it, those atoms of mercury will be attracted to the balloon, and they'll fly upwards towards the balloon.
So the charged atoms of mercury are attracted to the charge on the balloon, which draws them together?
Yeah, that's right. And then sometimes those charged atoms will bash into other atoms, and that will release a load of energy. And that energy is released as a kind of light called ultraviolet light, which you can't see. But if you've ever been in a disco or something, it makes your clothes glow.
Yes, I've seen that. When you're wearing a white T-shirt or a white shirt, it glows really brightly. So do your teeth as well.
Yeah, that's right. And then on the inside of the tubes, the white stuff is a substance which glows when this ultraviolet light hits it. And so that glows, and you can see it.
So lined on the inside of the light bulb is a bit like your teeth, so it will glow when UV light hits it. But why is it that when we hold the balloon still, it doesn't attract the charged mercury atoms?
Because you only get light released when these mercury atoms are moving and bashing into each other. So this only happens when you move the balloon towards it, and so they suddenly rush towards the balloon, or when you take the balloon away, at which point they'll suddenly repel each other and fly away again.
So is this how an energy-saving light bulb works normally when you plug it into the mains?
Pretty much, yes. You attach the mains across the tubes. You get electric current flowing through that tube, which moves these mercury atoms around and bashes them into each other, and you get the light released.
Fantastic. So you can light up a room almost using a balloon and an energy-saving light bulb. Do you think next time you have a power cut at home, you'll grab a balloon quickly and rub it on your head and hold it near your light bulb?
Yeah.
Are you sure you wouldn't rather use a candle or something like that?
I'd probably prefer a candle.
Well, I'm glad that we've been able to shed some light on this issue, but that's all for Kitchen Science this week, and we'll be back very soon.
Thanks, guys. So there you go. Waving a charged balloon near an energy-saving light bulb actually makes it light up. How fantastic. One for you to definitely try at home.
It is The Naked Scientist, thank you, Helen, with Chris and Helen. And here's a question for you, Chris Davis. It's from Stephen Broyles. He's Professor of Biological Sciences at State University of New York, and he says he sends his students out into the field to do biology and ornithology recordings of various birds and things with parabolic reflectors on their microphones so that they can record their sounds that they're picking up. And he says every now and then a student returns with a recorded tape that's picked up some music or a distant radio station. Where's that coming from?
That's very interesting. I guess it all depends on what frequency their equipment's working at, but the radio stations are reflected off the Earth's ionosphere, which is an electrified layer on the edge of space, which is where the aurora interferes with. And the ionosphere by night can reflect radio stations over large distances, and during the day they're much more absorbed in the lower atmosphere. So it sounds like if they're going out around dawn, it might be just around the time that these radio stations are changing, and they're picking up signals from a distance where they wouldn't normally expect to.
Thank you, Chris. Just a very quick one. Catherine phoned in about our kitchen science, and she said that she found the balloon burst, but she did see flashes of light. So, yes, that worked. Well done, Dave.
Excellent. I've got an email here from Daniel in the States who wants to know, when we're out looking for habitable planets in the universe, they're always a long, long way away, so isn't it possible that by the time we actually see it, or for that matter, get to it, it might no longer be somewhere where it's worth living? Have scientists accounted for this? Stuart,
what do you think,
any thoughts?
Well, it's certainly possible that if you're looking for planets in just throughout the whole galaxy, for example, you've got about 100,000 light years or so. To imagine the size of telescope you'd have to build to actually see a planet 100,000 light years away, though, is just so large. And all the ones we're going to look at will be only a few tens of light years away, so we should be okay.
But there is theoretically the possibility that we could pick up a star which turns out that it's going to have some kind of habitable planet around it, but by the time we get into the point where we can see anything useful, that star could have blown itself up.
Yes, the upside is that allows us to do cosmology, because the further we look back into space, the older the objects get, so we can do the archaeology of the heavens with that.
Are people looking at that then? Are people looking at things and literally, well, I suppose we are. We're looking at supernovae and stars that are blowing themselves to pieces, and we're seeing the deaths of stars which probably happened a long time ago, aren't we?
Absolutely, and that's exactly how you do galaxy evolution, is you just look for galaxies further and further away and know that that's how they looked billions and billions of years ago.
That's Stuart Clark. Thank you very much, Stuart. Well, that's it for this week. I have to say a very big thank you to our guests this week, Stuart Clark, Chris Davis, Pamela Gay and Terry Sloan. Also to our production team here at The Naked Scientist, Helen Scales, Ben Valsler, Tom Simpkins, Diana O'Carroll and Dave Ansell. Next week, we'll be looking at the homes of the future. We're exploring the science of sustainable living with a look at solar electricity generation, houses that don't need heating, and a gas boiler that also generates your electricity all for free. See you next time.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.